Alright, hello, my name is Giovanni Zavalza, and today I'll be trying to generalize general relativity. And so here is the Zavalza visual, and so I pulled it from about 3 different visual aids trying to demonstrate general relativity, and I've kind of twisted it and tried to make it my own to try to explain it in the simplest way possible. So, these pencils each represent a moment in time, a blip in time. And time is comprised of one dimension, and we only move forward. We do not move backward, we do not stand still. That would be manipulating time or time traveling. Now, we move through in a continuous motion, and it feels like it's continuous, but really, each time coordinate is composed of a single moment. Think of a video in which it's made up of multiple frames, multiple still images, and you compile them all on top of each other to create one continuous, what we perceive as the real world. So now to get into this fabric, as of right now being completely flat, completely straight, represents special relativity. General relativity is when the paths become curved. So I'll represent that with this hat. Now, as we move through time, in that continuous accumulation of moments, we move through space as well, or we can. So moving this way means moving through space, and moving up means moving through time. Now, this quarter, standing absolutely still, moves through time, but does not move through space. It follows this white path. It ends up here. We add the hat. The hat has gravity, and so now the path becomes curved. So now I follow from the same initial position with the same amount of time. We follow the path, the curved path. This path is a geodesic, and that is the shortest curved distance you take to get to your end destination. And we always have to go to this exact destination in time. We're moving forward through time. We cannot change that. So we take the shortest path to that time, that being this curved path. If you look at a flight, you would think that going straight on the map from one place to the other is the shortest path, but really it is a curve, and I pulled one from online showcasing this, and that's a geodesic, taking the shortest path. And so I cannot fully represent that because space-time is 4 dimensions, and we are 3-dimension beings. Just like a map is 2 dimensions, it cannot fully represent the 3D sphere of Earth. And so that's why there's that curve. There's also this curve in space-time, and honestly, it's like basically impossible to visualize. So I'll try to explain it, because while we cannot see how it happens, we can see what comes of it. And we can see here that these 2 quarters are in different blips of space at the same time. Now, normally in Newton's world, we would assume that that's because this thing has a gravitational force pulling it, the quarter, towards it, and so it moves through space that way. However, this quarter moving through space, I'll take a different quarter, moving through space, taking the shortest path means it has no acceleration. That's what Einstein argues. So, if we put this hat down, and we have quarter 1 moving through space-time, following the curve, it would end up over here towards the core of Earth, the center of Earth, where the gravity is pulling it, and where the space-time, geodesic, whatever, converge at that center. However, in reality, it tries to fall to the center of Earth, but the surface of Earth is pushing against it, pushing upwards. And that force is normal force. And so the quarter, trying to go to here, trying to take the shortest path that has no acceleration, has a different space coordinate than this one. Yet this one, once it hits Earth, has no spatial acceleration. Now, there's an Einstein formula, yikes, that shows how we can have no spatial acceleration, yet have a space-time acceleration. And so the a to the r is basically Newton's translational acceleration, and then everything to the right of it is space-time stuff. I don't even understand it. We'll skip that. But essentially, we could have our ma, the a to the r, be 0, yet our acceleration be not equal to 0. And so I'll explain. In this 2D surface represents an astronaut in deep, deep space, right? As he moves through time, his space-time does not change, or his space does not change. He does not move through space, only through time. So, if a rocket starts pushing at him upwards this way at 9.81 meters per second, as he moves through time, he'll also move through space. And Einstein argues that is the same on Earth. Even though we can chuck something in the air and it comes back down, it lands flat and it's not moving through space, we can say that this quarter right here is accelerating by standing still. How can that be? Well, when you're falling, just like this quarter right now, falls down, it feels weightlessness. And if a human was doing that, you would understand that feeling. If you ever jump high on a trampoline or other stuff. In deep space, you also feel that weightlessness. And that weightlessness is not feeling any acceleration. So when you're falling, you are actually experiencing no acceleration. That's what Einstein argues. Alright, so Future Giovanni here, but I'm playing this game called Outer Wilds. It is a physics simulation, probably my favorite game ever. But within here, you can see a spaceship floating in space, and me, like moving myself around. On the bottom left, you can see like basically a force diagram, but it's like each thing is one of my thrusters, so I could move myself around with this. But you can see that in this spaceship, it looks like we're not moving at all. We're just moving straight through space, kind of like you saw in my diagram earlier. But I could do any test I want here, and I cannot figure out the speed at which the spaceship's traveling. And you can see there that I was actually traveling at 21,000 meters per second, yet it looks like we're standing absolutely still within my point of view, which is also known as a reference frame. And so this kind of reference frame in which none of us are accelerating is called an inertial reference frame. And so here is another inertial reference frame. You can see that we're traveling 2,000 meters per second this time. That means we are moving at a tenth of the speed before, yet our acceleration's still 0, meaning, yeah, it is an inertial reference frame. And so at the bottom left, you can still see that force body diagram, in which I'm still applying the same force, and yet I'm still moving the same distance away from the ship each time or towards it. And I look around, there's nothing nearby to cause an acceleration on me. There's no electric, magnetic, or if you believe in the graviton, there's no particles nearby that could create a force that can change my kinetic energy. And so here's again another inertial reference frame, and this time you can try to guess the speed at which I'm traveling, and unless you look at the sun indicator at the top of the distance, the position changing, then maybe you can calculate the velocity. But if you ignore the sun, there's no experiment you can conduct here to prove that our acceleration is that our velocity is a definite number. So I'll go back into the spaceship, and remember that we cannot prove with any method using physics that our velocity is right here, the big revelation, 5,000 meters per second. There's no way to prove it. And so here, now there really won't be any way to prove our velocity because our sun is about to go supernova. And so we lose the one thing we can compare our speed to, but we also lose our solar system, our home, and everybody we ever knew. Our species is annihilated. And so right now we're still in deep space alone, and this feeling, not loneliness or dread, but the feeling of weightlessness is what Einstein cares so much about. So Einstein argues that this feeling of weightlessness right now in this deep space where we're all alone, uh, nothing applying a force to us. Clearly, I think we could all agree that nothing's pushing us in any certain way, that this feeling is the same feeling we feel on Earth when we're falling off a building or trampoline or whatever. Uh, so because of that, and we feel weightless in deep space, and there's no acceleration in deep space, then when we feel weightless on Earth, that must mean that there's also no acceleration there. And so another way to think about this is uh, when we're in a spaceship and it's traveling, let's say, away from our solar system at 9.81 meters per second squared. If you're inside the spaceship, let's say you just wake up one day and you're inside this tin can of a container, there's nothing you can prove so long as it's 9.81 meters per second squared. There's no way you can use physics to prove that uh, you are leaving Earth or you're leaving our solar system. You cannot distinguish that from the gravity of Earth. And so, because of that, there's no distinction between the two, then they must be the same. So, the falling on Earth is the same as floating in deep space. There's no force being applied to you there. But the spaceship pushing up on you at 9.81 meters per second squared, its normal force, in which when you throw a ball up or when you jump up, it accelerates towards you at 9.81 meters per second squared, is the same on Earth, and you can treat Earth as a giant spaceship itself, where when you jump, it travels towards you at 9.81 meters per second squared. And so it seems strange that you can accelerate while standing still on Earth's surface, but again, I demonstrated with that formula earlier, the situation. But uh, now that we have put that thought into your head, now we have to prove that it is more sufficient than Newton's uh, force mechanism. And so we can look at Mercury, and so Mercury is obviously very close to the Sun. It orbits in an elliptical pattern that shifts every time it makes an orbit. It moves, like if you're looking at it from a bird's eye view, if it was like, it moves like counterclockwise around the Earth. Its long path travels around this, like orbits around the Sun in like a flower petal, if you know about Calc 2. And so, as such, when the scientists were trying to prove how Mercury travels in Newton's gravity, with Newton's mechanisms, it failed. And it failed because the gravity from the sun is so powerful, there's so much of it accumulated, that uh, Newton's gravity mechanism doesn't work there. There's just too much gravity there. And so scientists thought, okay, well, Newton's gravity has to work. It works on Earth, so it has to work on there. They thought that another planet was pulling Mercury and it would adjust its speed and path uh, from that planet. And so they were looking for that second planet, and they were so confident that this second planet, which they named Vulcan, existed because that's exactly how Neptune was discovered. Uranus followed a different pattern than originally calculated, and so they thought, okay, well, the force of gravity has to work out, so there's got to be another planet that's pulling Uranus. And there was, and it was Neptune. And so they started looking for Neptune because of Newton's force mechanism. But it fails here because this mechanism doesn't work when there's so much gravity. And so here comes Albert Einstein proving with his general relativity formulas that Mercury is following the correct path that physics dictates. And so, if you need more general relativity proof, you have seen photos from the black hole, I'm assuming, not just the one we found like 2 or 3 years ago, or the Event Horizon Telescope people found, but also
the one at the center of our galaxy in the Milky Way. It's just been revealed like last month, so good timing from them. But uh, that proves that Einstein's general relativity holds up. And so, because of that, uh, it seems conclusive that we can rely on Einstein's general relativity. And so, I could end the video now and talk about how I have all the answers and figured everything out, and general relativity is superior. Uh, it really is not. And while it is the best we can muster right now, with top scientists not being able to prove it wrong, uh, it still likely is very far off from the true explanation of our universe. It has predicted black holes, but it fails to completely explain how the thermodynamics and angular momentum and other things that are really complicated and I don't know about uh, can still exist and not break fundamental principles and rules of our universe. And so it can work on really grand scales with the sun and galaxy and even universe. It fails to explain on a microscopic level where quantum theory prevails. Is prevails the right word? Where quantum theory works. And so because of this, uh, it doesn't have the full truth. And so even now, when we're so far advanced in physics, we're still not 100% certain of the truth. And while general relativity is the best we got, there's lots of evidence telling us that there's still more to develop on it, or it can be proven entirely wrong yet again, just like how I just proved Newton's force mechanisms don't fully work when gravity's involved. And so, because of this, I want to leave you guys with the reality that science is still a process. Even though we feel like we've come so far with figuring everything out, there's still so much more to discover, including like the dark matter and dark energy and stuff. But there's still so much more to learn and ponder on and prove. And so while back then people thought that the Earth was at the center of the universe, there's people now who believe we are at the end of time where we, as a species, we learn everything there is to learn about. It's just not the case. And it's happened time and time again where some small group will think of, conjure up some random idea, whether it had lots of evidence or not, still proves, or it gets proven correct even thousands of years later. Uh, Really quick, before I end the story, or video, I'll explain a brief story with Aristotle, Plato, and this random dude. Now, this random dude's smart, but I forgot his name, so I'll just call him random dude. But Aristotle and Plato were two philosophers, scientists, and even uh, physicists to an extent, with Aristotle uh, proving or trying to thought experiment out Newton's inertial stuff, where he would talk about friction and the more smooth the surfaces, the more an object slides. And so he had all this knowledge about what he thought was the universe, yet when it came to what made up the universe, he thought it was made of different components of fire, water, earth, and air, the four elements. And this random dude said, no, we're made of tiny, indestructible particles, tiny thingies. And uh, Aristotle and Plato disagreed, and because Aristotle and Plato disagreed, everybody agreed with those two. And so, for hundreds and even thousands of years, until I think it was either the 1600s or 1800s, when the atomic theory finally came up again and it was proven correct that this dude was ostracized for that whole time and people didn't agree with him. And so, I want to end the story with that we don't know the whole truth and we could be really far off. And so, I thank you for watching the video, and I appreciate you taking these 20 minutes to hear what I have to say. And I'm sorry I didn't really have a script or anything. It's my first video, so I'm learning. But thank you for listening to this video, with the takeaway being that science is a process and we still have to figure out all there is to the universe.